My name is Numer, and in this video, I will be talking about our work on metamorphic testing of Datalog engines. This work is in collaboration with my advisor Maria Christakis and Valentin Lustholz. Datalog is a declarative, logic-based query language which is essentially a subset of Prolog. It is expressive yet concise, and as a result is used as a domain-specific language in several application domains such as natural language processing, bioinformatics, big data analytics, networking, program analysis, and security. Datalog query evaluation is performed by Datalog engines, prominent examples of which include Souffle, LogicBlocks, BDD, BDDB, DDLog, and MuZ. Unfortunately, as any complex piece of software, Datalog engines may contain bugs, resulting in incorrect query results. An incorrect result may manifest itself by including wrong entries or by missing entries that should have been included. We refer to these bugs as query bugs. Depending on the application domain, query bugs may have detrimental consequences. In particular, when a buggy Datalog engine is used in program analysis, it could compromise the soundness of the verification process. In other words, it could cause an analyzer to verify incorrect software. In this paper, we present the first automatic test case generation technique for detecting query bugs in Datalog engines. A major challenge in finding such bugs is the lack of an oracle specifying expected query results. The problem may be overcome with the technique known as differential testing. Differential testing would involve running multiple Datalog engines on a common set of programs and comparing the results for discrepancies. In our context, this would be difficult as there exists no unified standard for Datalog syntax, and as a result, many different dialects have emerged. Our approach circumvents the lack of an oracle using an alternative technique, namely metamorphic testing. It works by transforming a Datalog program such that the result of the transformed program has a known relationship to the result of the original program. Example of such a relationship is that the result of the new program should contain the result of the original program. To ensure that these oracles are known in advance, we designed metamorphic transformations based on concepts in database theory and in particular the formal properties of conjunctive queries. Before we dive into some of these transformations, let's quickly take a look at some background. Datalog is a logic programming language where programs comprise a finite set of rules over relations. Input relations are given in the form of facts. They are also referred to as extensional database relations or EDB. Intentional database relations or IDB are defined by logic rules, and one of them is specified as output. These rules define the IDB relation reachable, which computes the transitive closure of the input relation edge. Pictorially, edge represents this graph. There is an edge from node x to y if edge xy is a fact. Execution of this program is essentially a sequence of derivations where each step adds an edge tuple to the output relation reachable until a fixed point is reached. These are the final tuples in the reachable relation, which is the transitive closure of this graph. We designed our metamorphic transformations based on the formal properties of conjunctive queries and in particular query containment. A conjunctive query is a single, non-recursive, function-free horn rule. This is the simplest type of query that can be expressed over a database schema. Syntactically, a conjunctive query is an expression of this form, where u and ui are vectors of variables and constants. Any variable in u must also appear in some ui. The expression to the left of the arrow is called the head of the query, and the expression to the right is called the body. Each RI/UI in the body of the query is called a subcore, where Ri is a relation. Two conjunctive queries Q1 and Q2 are equivalent if for every database instance the result of Q1 is equal to the result of Q2. Q1 is contained in Q2 if for every database instance the result of Q1 is a subset of the result of Q2. It is easy to see that if Q1 is contained in Q2 and if Q2 is contained in Q1, then Q1 and Q2 are equivalent. Now, given two syntactically different conjunctive queries Q1 and Q2, how can we tell statically if Q2 is contained in Q1? So consider these two queries. A decidable procedure for checking query containment involves determining whether there exists a so-called containment mapping between the two queries. In simple words, Q2 is contained in Q1 if there exists a mapping between the variables in Q1 to the variables in Q2, and we can use that mapping to map each subgoal in Q1 to any subgoal in Q2. So for example, the variables in Q1 are w, x, y, z, and Q2 contains only x and y. Now there exists a mapping from the set of variables in Q1 to the set of variables in Q2, and we can use this mapping to map all subgoals in Q1 to subgoals in Q2. On the other hand, Q1 is not contained in Q2. This is because there doesn't exist any mapping between the variables in Q2 to the variables in Q1, which will allow us to map all subgoals in Q2 to a subgoal in Q1. For example, let's say we map x to x and y to y. With this mapping, we can map head subgoal to the head, axy to axy, but now we can't map ayx to any subgoal in Q1. In fact, there does not exist any mapping between variables in Q2 to variables in Q1, which will allow us to map all subgoals in Q2 to a subgoal in Q1. Therefore, Q1 is not contained in Q2. Alright, so now the question is, how can we use query containment and query equivalence to design metamorphic transformations for Datalog programs which will allow us to test Datalog engines? Consider the same program we saw a little bit earlier. To keep this presentation simple, I will explain a single transformation to a single rule. However, in practice, our approach can perform sequences of transformations to multiple, more general rules. Let's consider, for example, the last rule of the program, and let's take a look at how the ModCON transformation works, which is one of the 8 metamorphic transformations we present in the paper. Due to time constraints, I will not be able to talk about all the transformations in this video, but I encourage you to check them out in our paper. The ModCON transformation transforms a rule while modifying the variables in the rule, and it ensures that the result of the transformed rule is contained in the original rule, so essentially contracting the results. So given a rule, the transformation modifies a variable such that there is a mapping from the variables in the original rule to the variables in the transformed rule, but no mapping from the transformed rule back to the original rule. This ensures that the result of the transformed rule is contained in the original rule, but not the other way around. In other words, the result of the transformed rule should now be a subset of the original. Let's now take a look at another transformation called AddEQU. This transformation adds the subgoal in the original rule while ensuring that the transformed rule will be equivalent to the original. So given a rule, the transformation adds the subgoal with possibly new variables, and it ensures that there is a containment mapping from the original to the transformed rule and back, thus ensuring that both rules are contained within each other and are hence equivalent. Using the containment properties of conjunctive queries, we designed 3 general metamorphic transformations, namely add, mod, and rem. In add transformation, a rule is transformed by adding a subgoal, in mod by modifying a variable, and in rem by removing a subgoal. And these transformations either expand the result of the transformed rule or keep it or contract it or keep it equivalent to the original rule. This information solves the oracle problem for us, and if we now get an unexpected result after running the transform program with the Datalog engine, then we can be sure that we have detected a query bug in the engine. One important thing to point out here is that our approach generalizes from a single transformation to sequences of transformations and from a single conjunctive query to full-blown Datalog programs. So finally, bug detection works as follows. Given the Datalog program, we transform the original program using our metamorphic transformations and compare the results of the original program and the transformed program using the corresponding metamorphic relations. If for any result pair the metamorphic relation does not hold, then we can be sure that we have detected a query bug in the engine. We implemented our approach in a tool called QueryFuzz, which is open source and publicly available in GitHub. With QueryFuzz, we were able to detect 13 unique query bugs in 3 popular Datalog engines. All query bugs were confirmed by the developers, with a few bugs exposing deep semantic issues that cannot be easily addressed. A souffle case study showed that the detected query bugs revealed issues in all components of the engine. All the metamorphic transformations we proposed in the paper contributed in detecting at least one query bug. You can find more information about the remaining transformations and how we lift our oracles from individual queries to full-blown Datalog programs in our paper. Thank you.